Here we are.
Yes, my engineering comrades. Hey, I just went into my open math and I posted today's problem because I do want to give you guys some time to try to wrestle with it. I think if you do that before I show you my answer to it, I think you'll get more. Like whatever you do wrong, then it's like what I say will teach you. I'm a little concerned just because the average score on this test, this particular unit was a little more painful than ones we've had before. So I'm going to pull it up. Maybe you pull it up too.
Is that a 16101?
Yeah, I put it way down at the bottom, just right in plain sight so you can see it. So yeah, it's not in a file. So
yeah,
should look like this. If we go into practice mode for the test, then let's make this our first. Let's make our first calculation for this. Thinking of this like review. As being velocity. Now I'll have this up. You don't have to. It's just nice to have a picture in front of you when you do this. But let's all get the velocity right first. If I just turn you loose for that. And I'm interested. The first thing I'd like you to do is think through our equation for this. Because I don't want to do any of this for you. I want to do it after you do it. But I want you to think about this. So if C is the driver, of course, the question really becomes then for velocity, like, okay, well, then what is B doing? This is the whole idea of the fact that this is like connected motion, relative velocity. Oh, look, C has a velocity 4. Well, oh, look, it's connected to B. And so B is going to have a velocity. So what is that velocity? And so does that concept drive your understanding of our basic formula then, where we say, oh, well, it's V. What's V of B then? That's our question, right? Well, it's equal to, you have A, you have this in your note sheet, plus so again, I want to draw this for you. So, okay.
Right, so
you agree that in the steps of this would be B prime. In other words, there's what velocity of B does first, is it just does whatever A does. But then secondly, it has to rotate back into position, right? This is what I'm hoping is sticking with you. In other words, the very next thing this thing has to do is rotate back into position, because that's where B is actually going to be. In other words, that's B like double prime. B started out and then it went to B prime, then it went to double prime. And so the second part of this equation is the velocity of B. I'm sorry, I called that A. Why did I call that A? If this stuff isn't confusing enough, I've got to the letters wrong. So V is the driver, right? So whatever the velocity of C is, that's what the velocity of B is doing. But then secondly, B is going to rotate around point C. Like that's our basic equation. Again, you don't have to have that memorized. But my question to you is, and I want you to get this right before we start, can you draw in where the velocity of B goes? So we have the velocity of C, that's sitting right here. But where in the drawing, where's the other things we don't have drawn in, which would be the velocity of B and the velocity of B as it rotates around C.
Well, direction-wise, velocity B really only has one way it can possibly go. It has to be moving tangent to the circle.
Correct. So does it make sense that that can only either be that direction or that direction? Like that's the only one. And that's why it's important to like stare at this picture and read it out. Get it drawn the right direction. Otherwise it's going to make your drawing look weird. And that red, the red translation that happens first is exactly, tells you exactly that. It tells you what that's doing. It's moving to the right. So it's not this one. But I'd be willing to bet. So you say, okay, cool. I know where the velocity of B is. It's going to actually go that direction, tangent to the circle. But what about velocity of B as it rotates around C? If you can't draw the second part of what I drew, if you can't visualize that, in other words, visualize the fact that this bar here, if you will, this bar BC is actually rotating clockwise in order to stay, in order to keep B on the circle, which is where it's going to have to stay because of the connecting arm BA. If you can't visualize that, then you're going to get this wrong. Where does that velocity go?
To the right and down, I mean 90 degrees from the line CB.
That is exactly right. Do you see that that's hard? In other words, this is where it is. So I kind of have to, if not draw it in, actually, you know, fully draw it in as I did, I've at least got to visualize that happening, or I'm not going to get these correct. So the fact that, come back, the fact that that is 90 right there, and that this is 90 over here. Like you have to start these problems with that drawing drawn correctly. Do you agree with me that it would be very easy for somebody to kind of draw this over here?
My natural inclination here, honestly, is to kind of leave VBC alone until I can take it out, like just find it mathematically instead of including it into my drawing early, to be honest.
I have no problem with that. Yeah, I have no problem with that.
Because it feels like it's just kind of a dangerous thing to be doing.
Yeah, but remember though that VBC is at some angle. That's the problem with these questions, is it's at some angle and you've got to, you know, multiply it by the cosine of 39 degrees or 70 degrees or 62 degrees. Like you got to multiply it by something. And if you don't have it drawn in the picture correctly, you might get that wrong, because notice the red one is going up and to the left, which means X is negative, Y is positive. Whereas the green one says, no, it's actually going to the right and down. And so X is positive, Y is negative. And so although that won't screw up your answer because it's still going to be the right size, it will screw up the sign of that answer. And that may cause you, if it's negative when it should be positive, to be subtracting when you should be adding. And so I think the picture helps whenever you get it in there. But at a glance, I mean, don't you see B is moving? Don't you see B is moving in this direction? So doesn't it seem like that would be the direction that B of C would be going? Isn't that weird that it's kind of not going the direction you think it would go? So,
it kind of makes sense, actually.
Yeah, I mean,
it necessarily has to be. I guess if you consider, God, I don't want to think. Do you consider VB to be in the, well, let's just set our axis of VB to be our x-axis. Then we know it has to have a component that's in functionally in the negative y to keep it on the. Actually, that doesn't make sense. No,
It's hard, isn't it?
yeah. Never mind. I thought I had it all figured out, but
You're
never
proving
mind.
my point. I mean, this is really hard, isn't it?
So how I'm thinking about this, that shaft AB, that's what keeps it in the circle.
Correct.
So it should push opposite way from direction of C. Pretty much, it should go opposite direction. So it should keep it on the circle, because if it's gonna go same direction, it means it
Yeah,
follows the C. That's how I'm thinking about this.
But notice one of the, the big takeaways, like if you were just to ask your own questions about this and say, what's interesting about this? Well, you look at C and you say, hey, it's moving to the left and it's stuck in a tunnel. So it's just going to go straight left. Okay, cool. But what else is going to move as a result of that? Well, notice one of the interesting questions is, what is that? Which is the speed of B as it rotates around C, or just BC. I mean, again, I like to write it like that instead, but that thing is going to have a rotation to it, a rotational speed to it. That's kind of cool that you can figure that out. That, I think, is a really interesting takeaway. Maybe V is an interesting takeaway, but I think far more interesting than the velocity of B is this over here, which is actually the rotational speed of B as it moves around A. I mean, those are the two interesting things, because in the end, the one I just wrote right here, that one is actually the motor turning. Do you see what I'm saying? I mean, that's an RPMs of a motor. So if you were to ask one question that's interesting here, I would say, this is less interesting, but the rotational speed, the angular velocity of BA, that's like the main takeaway here. I got this thing shooting along, cool. What kind of RPMs is that going to cause up there at that crank arm? That's the whole point of doing this. So there's interesting questions we can ask, but that's the main one. So we still get to review for the test, but so you take it from there. I'm going to give you enough time to get your answers for velocity. Notice this particular question is ultimately saying, let's talk about acceleration. But remember, we said yesterday, we're going to need velocity anyway. So why don't we, as I probably will do on the test, why don't we let's find this first. Let's pretend I asked the question. Tell me everything about the velocity. And ultimately, I'm going to answer all the questions I just answered. What's the speed of B? What's the rotational speed of AB? What's the rotational speed of CB? I want to know all three of those. I find those all interesting. I don't know if I'll need them for other things, but I don't care. They're just interesting. I'll give you a minute.
So it looks like we have to convert maybe distances from inches to feet, or our velocity and acceleration converted to inches per second.
Yeah, that's annoying, isn't it? Actually didn't intend that to be a pain, but what shall we do?
I already did. So AB is 1.25 feet and BC is 3.25 feet.
Okay.
Yeah, let's go ahead and go with that. And that's the last thing I want to do with these questions, is throw in something like that and have you miss it. So on the test, I'm not going to mess with the units at all.
Yeah, this ties into a lot of what I was having trouble with in the homework, doing it more normally. My usual approach was just to turn VBA and break it up into the cross product of the angular velocity and the position vector. But we don't have the angular velocity here, and it's kind of the way that AB is constrained makes it kind of, there's got to be a way to do it. I just can't. I'm not sure how to do it.
Mm-hmm. You're basically trying to think, is there some way I can automate this process so that I don't have to think about signs, I don't have to draw pictures, and good on you, for thinking like that. honestly, I'm not as smart. Like I kind of need to see it, draw pictures and so forth. So, but certainly if this is your job, we got to figure out how to automate this process a little bit. So yeah.
Like, let's see. Hmm.
I'm gonna stop sharing for just 1 second here.
There it is.
Or you got 28 degrees for velocity BC. I mean, working with 28 degrees for the BC, velocity BC. Did someone got that?
Maybe I'll,
Uh,
I was trying to decide if I should, let me see if I already have this worked out.
let's see, 62 plus 70.
Did I already do this?
Yeah.
Looks like I did. All right, I'm looking at it. What'd you say, Evelyn?
I said 28.
For an angle?
Yep.
Yeah, there is a 28-degree angle.
And the other one is, let me see. And the other one for VB is 20.
Yep.
Okay.
Yeah, so what you're saying based on the modifications that need to be made, which is really important, is I need to know what angles those are at. And that's rough. But I will say this, one of the easiest ways to get up here is like this angle down here is 62. And so if I extended this up, does that make sense? This is also 62. That's one of the easiest ways to get up there.
Hmm.
And then since the red and the green that I just drew from here to here is 90, then that's exactly why this angle's got to be 28. And by the way, notice, well, I guess I should leave it at that. So, and so the same thing happens with the other one. In other words, if I extended this up here, since theta is 62, then that means this would be 62. I'm sorry, 70. Theta is 70. So then again, there's a 90-degree angle there. So that makes this angle 20 degrees. So I don't know how you got up there, but that's one of the easiest ways to get up there. So that's your, so I didn't have to draw triangles and, you know, that can look really complicated, but it's really not. So the fact that this red is your velocity of B in X, and this Y right here would be your velocity of B in Y. I think it's kind of nice to draw those in to kind of see the right triangle there so that you understand that this being the velocity of B, now that I kind of think, now that I'm thinking of that as the hypotenuse, that's kind of a lot better way to draw this. If I jump over to the other side, the fact that this is my velocity of B with respect to C in X, and this is my velocity of B with respect to C in Y. And now I am thinking of that as being more like the hypotenuse.
It's 28.
So it is important to understand that right now, because I drew my drawing correctly, does this make sense to you guys that every one of these is a positive number? Because we're talking about rotational, and rotational is positive in the direction it's traveling. And because I took the time to conceptually understand what's happening up there and I drew them the correct direction, then those arrows are in the direction they're going to be traveling. Therefore, all of them are positive. But now when I switch to a different coordinate system, not a rotational coordinate system, but to an XY coordinate system, now the fact that X's are positive and negative and Y's are positive and negative, now that all comes into play. Does that make sense? So the hypotenuses are always positive if you draw your picture correctly. I don't think that's obvious. Have I given you enough time to write the equations down just so you can compare them to mine? Because I don't want to write anything down that you guys haven't already written down.
I'm almost got a velocity BC, almost there.
I am not at all taking the same approach, so we'll see how this goes.
And again, when you stare at that, you should think, oh crap, 2 equations, 6 unknowns. Not good. But you can replace the velocity of bx and the velocity of by with trig. So I can replace velocity of bx with just the velocity of b, except that would have to be modified by the cosine of 20 degrees. And it's going left, so that I have to be negative. And b is the same thing, except for it would be sine in the picture. So velocity of b times the sine of 20, and it's going down. Do you see that that just accomplished? I no longer have 2 equations and 6 unknowns. I have 2 equations and 5 unknowns because I rewrote those 2 separate values just as sort of functions of velocity of b, because that's all I ever wanted to know anyway. I didn't want to know the velocity of bx and by. So that's what I'm going to try to do.
Really quick question. You got for BC velocity 1.84.
Yes, I did.
Okay.
That's a good sign. Means you do all this right. Notice the velocity of c is moving in x at 4, and it's moving left. Whereas it in the y direction, because of its constraints, it isn't moving in the y direction at all. There, I just got rid of 2 more unknowns. Now it's actually 2 equations, 3 unknowns, because those were constants. That's even better. And then BC is going to behave exactly like B did. I say, well, what's BC doing in X? Well, that's the same as the velocity of BC, but it's modified by the cosine of 28 degrees. And it's right, so it's positive. And this is down. Velocity of BC, not with a Y, modified by the sine of 28, and it's moving down. Mission accomplished. I now have 2 equations, 2 unknowns. So I'll stop there for a minute. If I stick those in the matrix, I get the velocity of B as 2.53. And the rotational velocity of BC is 1.84, as Neville just said.
So now to find WBA, do we have to use velocity of B and the radius of BA? Is that what it is?
That's exactly right.
Okay.
So can you appreciate that the velocity of BC is Not something that anybody would ever want to know. Whereas the rotational velocity of BC, in other words, the rotational velocity, again, that's angular velocity of B as it rotates around C. I think that's pretty interesting. And the same for AB, the angular velocity of B as it rotates around A. And of course, our driving equation for this is the fact that linear velocity is angular velocity multiplied by r. So that would mean that this is the velocity divided by the radius. But again, the velocity of what? Well, that's the velocity of B. And this is the radius of BC, since we're talking about that rotating. Yeah, maybe it's. So what's wrong with the statement that I just wrote? So I'm moving down here and then I think, well, wait a second, that's velocity of B as well. But that'd be the radius of BA. So it's like, what? Which velocity? Which velocity am I using here? How do you tell? They can't both be velocity of B, but aren't they both talking about B moving? They are both velocity of B.
So if we're talking about WBA, it should be a 90-degree velocity coming out from that radius.
Yeah, in other words, it's the one perpendicular to that radius. Does that make sense? Now we say up here the velocity of B, but does it make sense? You could just as easily say velocity of B as it rotates around A, because isn't that what's happening up there? That B is rotating around A. So for that reason, this first one is BC, so this is the velocity of BC. The second one is rotational around B around A, so this is really B around A. So what Evelyn said is exactly right. You got to look to see which one it's perpendicular to. Whatever radius you pick, then it's the velocity that's perpendicular to that. And of course, these are all known now. Found velocity of BC, 1.84. Again, notice units, feet per second. And then the radius of BC, fortunately I was given that, as you would be, which is 3.25 feet. When you divide those, you get 0.57. Again, as I've said before, the feet cancel and you get nothings per second here. Which is weird, isn't it? It's like, so it's radians then, like you don't have a choice.
Shoot.
So down here, similarly, you get 2.53 feet per second, and that radius was 1.25. So you end up with about 2.02. Really armed with those four numbers, the two velocities linearly, and the two velocities angularly, you kind of own the velocity behavior of the whole system now. Like there isn't anything you don't know that a person might be interested in. Do you agree with that? Satisfying to you? Okay. Did I give you enough time with that, Landon? I think you stayed ahead of me, Evel, but did you guys all get those answers before I got them?
I didn't, but that's because I used a different methodology, and I'm realizing now that I did it wrong. I'm trying to figure out where I did it wrong. Or shit, no, never mind. I know exactly where I did it wrong, but it's gonna take me a while to redo it.
No worries. So we got velocity worked out. Let's see if we can get acceleration worked out. So in exactly the same way the velocity equation worked, BC, acceleration will work exactly the same. Acceleration of B is the same as the acceleration. If we want to know what the acceleration of B is, it's going to be the same as the acceleration of C, then with the rotational acceleration component to it. Again, these are given. I don't think we looked very much at my note sheet yesterday, but just since that's what you're going to have on the test, is that speaking to you? Just the right. It's not right. It's the calculus one. Yeah, we didn't look at this at all, I don't think, yesterday. So you might keep an eye on this just because that's what you're going to have available on the test. So then we are replacing, we said, that's our next move. We're replacing the angular acceleration with the fact that it has a tangential and normal component to it. So the ultimate equation is not that. It's ultimately that component, which is composed of a tangential component and a normal component. So there's our equation. So we want to know what's happening at B, question mark? Well, it's what's happening at C plus the rotational component of what's happening at C. But the rotational component has a normal and tangential component. So the question is, can you go back to your figure and get those in where they belong? Can you draw those into your picture? Tangential, normal. So this is the acceleration of B. But that's actually a change of speed. That's what tangential is. Normal is over here. Normal is a change of direction. And so that's the acceleration of B normal. Same thing with velocity of BC. Well, angular acceleration of BC is right there, but that's the tangential component. That's the speed change. Whereas perpendicular to that, coming down here, that's the acceleration of B with respect to C normal. Why is it important to have those drawn in the picture?
Directions.
Yeah, because I'm going to have to go horizontal and vertical in a minute. And just like we took VBX here and modified it by the cosine of 20 and so forth, I'm going to do exactly the same thing here. So I'm going to not be able to use acceleration of BC normal. I'm going to have to modify it by whatever angle that's at. Notice it's not an angle 20. Like these are like all at different, well, they're not all at different angles. Notice the tangential ones. The tangential ones are at 20 and 28 degrees. And so those are fine. But the normals are going in some new direction that I don't know what it is. I'm gonna have to get some angles involved. So again, I'll get this started for you, but I want to give you plenty of time to think about it on your own. The question is, can you write out the horizontal and vertical equation, and can you get those angles involved to try to decrease your number of variables?
I think that's where I'm getting really confused, because now we're talking about vertical and horizontal.
Yep.
But we're not taking, like, let's say, acceleration B, T, and we're not taking their X and Y components. It's just,
No, you actually are.
really,
Yeah. In other words, your first move here is to say, okay, well, great, horizontal then. So that means I rewrite that exact equation up above. It's just that I rewrite an X in every one of them. I'm not considering the acceleration of C, but the acceleration of C and X. I'm not considering the acceleration of B with respect to C tangent. I'm considering the X component of that tangent. And the normal, nope, not the normal, but the X coordinate of the normal. So the best thing to do is kind of like we did with the red, is just to give the angle from horizontal. So the 20 and the 28 still hold. But what about this acceleration of B with respect to C normal, what angle is that at? Where, how do I get that involved? Where? Well, I see 62 down here. And this horizontal is parallel with this one. So if this is 62, that angle up there is 62. That's what I've got. Like that angle right there is what I'm at. And that is a 62-degree angle. Again, that's the fastest way to get up there. You can play around with this and draw right triangles and all kinds of cool stuff to get this to work. And the same thing happens on the other side. So if this angle, this theta angle is 70, sort of between here and here is 70, then that means between here and here is also 70. So my angle from horizontal, that entire angle right there, 70. If you're careful to draw the angles as relative to horizontal, then that means your x's will always be cosines and your y's will always be sines, which is a way you can kind of check your work to make sure you don't screw up. Do you see how my x's are cosines and my y's are sines in the way that that just happened before? But if you make sure the angle that you happen to report is the angle from horizontal, not the angle from vertical, then that's kind of a cool way to just make sure you don't make a dumb mistake. I don't know if that makes sense to you. So what you should notice in the equations that you have written again is the same line of thinking, which is, oh no, I've got 2 equations, but I've actually got 4 unknowns in each one. So I actually have 2 equations, 8 unknowns right now. So I need to do the exact same thing I did before. Just start replacing those. I don't want ABX and ABY. I want just AB, but then modified by a sine or a cosine. I don't want ACX and ACY. I just want AC, but maybe modified by a sine or a cosine. If I do that with all 4 of those, that should get it down to 4 equations. I'm sorry, 2 equations, 4 unknowns.
So, I'm really inclined to break out the IJK notation for this and then start just
Yeah,
keeping a lot of stuff in vector form for this.
yeah, I really sympathize with that. I really
because I don't like that. I don't like this very much notationally. It's kind of really ugly.
Yeah. You're not wrong at all. In other words, what you're thinking of, I'm going to erase this, but what you're thinking of is let's not have 2 equations here. Let's just have 1 equation, and like this will be my X and this will be my Y, and then equals, and then I'll have another X and another Y, and plus another X and another Y. And this one will be my B, and this will be my C, and this will be my tangential. Absolutely. Knock yourself out. Accomplishes the exact same thing, and I think that's wonderful.
I was also just thinking, what?
For me, I can't automate and like speed things up until I've done it slow and boring kind of more than once. And then I kind of like, okay, I get that. And now let's think about kind of speeding it up.
Well, I'm just thinking we know that the acceleration tangent is just alpha times r.
Right.
It's
Yeah.
I kind of, in terms of, I kind of like having the what we were using the R vector, if that makes sense.
Yep.
The vector of, R of B over A, or in this case, R of B over C, but
Yeah.
because then it's just a cross product, and then I can run through that really fast. Then instead of keeping it as a vector, I'm inclined to just make it I and J components.
Sure.
And then though, like the I components are one equation, and the J components are the other equation. Because this,
Mhm. Yeah.
or I think I just hate typing this actually.
I 100% understand and agree with what you're saying. I mean, my problem is that as a teacher, if you're going to do that, I want you to do it because you're making that up. And I think that's good. But if I just showed you this mechanical approach, just take this number, stick it in this box, just take that number, stick it in that box, do the cross product, out pops the answer. Like if you ever need this in the future as an engineer, you won't have learned much conceptually. And you probably won't ask to do this, if that makes sense. So, what I'm more largely interested in is building a conceptual understanding of just how the world works. So the slow, I don't know, waste of time, but very visually accessible approach. So I'm not trying to talk you out of that because you're inventing that for yourself. I think that's absolutely awesome. But that's why I'm not showing it to you that way, so to speak. Let's see. So I'm going to replace a couple of things in this. So I'm looking at acceleration of B. I'm just starting on the left side of the equation. If I go back, unfortunately, I can't put these up so you can see them both at the same time. Acceleration of B. So acceleration of B in the X direction. Well, notice I have two. I have this and this. Don't those both make an X contribution? This problem is harder than yesterday. Those both make an X contribution. So I could say acceleration of BT multiplied by the cosine of 20. That would be an X component. And I see from the picture that's a negative number. But unfortunately, there's like more to that because isn't the acceleration of Bn also making an X contribution? Oh, I said 20. Yeah, that's right, 20. N's making a contribution to acceleration of Bn. That's also pushing left. No, it's pushing right. Does that make sense? It's right there. So it's actually pushing right, and notice it's at a 70-degree angle. So I'm going to take acceleration of Bn modified by cosine of 70, and that's actually pushing right. So that's going to be a positive. Wow. Does your brain hurt like mine? So acceleration of Bn times the cosine of 70 degrees, all of that. So that's actually worse because but I'm at least trying to pick kind of terms that I have in my pictures. Like that's actually making it worse. I got more letters than I had before. And while I'm at it, I think I'm going to go over here and do the same thing down below. In other words, isn't this also going to be acceleration of B tangent, but it'll be modified by the sine of 20, and acceleration of B normal, but it'll be most modified by the sine of 70. Now the question is, are those positive or negative? So I'm going to go back here and look at BN. So I'm staring at this and I'm thinking, oh, that's going right and down. So my X is positive, my Y is negative. So my Y was negative because it was going down. But what about what about tangent? Again, I'm only looking at Y. We'll notice it's also going down. So it's negative as well. So in other words, looking at the whole thing, I've got a negative X and a negative Y for my tangential component, but I've got a positive X and a negative Y for my normal component. Woo! How's your brain?
I don't like this.
Fair enough. That's very painful, isn't it? Isn't it weird that it's this complicated? Like, fortunately, what's happening at C is way better, because what's happening at C, we'll notice C is only constrained to move left and right.
What's that
So-
even? I forgot what I was even originally looking for here.
I know, yeah, you get told, you can forget who you are. What was my name again?
Angular acceleration like AB.
So it's going left. So it's negative, and it's not going up and down at all. So when I go down here, I say, okay, cool. Whoa. I say, cool, that's actually increasing nothing in the zero component, whereas the X is going left 2. So let's see, what do I have now? I still have 2 equations, but I have ABT, ABN, and I still have tons of X's and Y's. So I still have just stuff everywhere. I'm totally lost. I'm totally confused. But this is why it's so essential that your picture is good, because I'm going to have to go to the picture. I'm going to the picture right now to look for this guy. And I'm like Landon said, I'm staring at this thinking, I have no idea where that is. And so I'm looking at maybe both of these at the same time, because they're both tangential versions of BCT. One's X, one's Y. So I'm going to the picture. I'm sure hoping the picture is going to tell me what that is, because I can't really keep it straight. So, okay, cool. There's the tangential component. So I'm kind of staring at that. I'm thinking, what's the X and Y coordinate of that? We'll notice that's relative to the 28-degree angle. So the X is positive. So it'll be modified by the cosine of 28. And the Y is negative. It'll be modified by the sine of 28. So for that reason, I'm going to be able to rewrite these 2 terms as just BCT, but because this was X and it was going right, that would be positive, which I think I'll just leave off, but modified by the cosine of 28, whereas for the Y coordinate, it's also cool in the sense that it's modified by the sine of 28. but it was negative because it was going down. And so do you see how they just got rid of one variable? One was tx and one was ty, and now I just have abct, abct. I have one less variable there. And I don't know if you remember this, but this problem is worse than yesterday because we have a lot more angles. Yesterday, the snapshot in time, and you may notice too that your book assignment does this, makes this a lot easier on you. Then this is like a terrible problem because I put B here, not at the top. B is angled over a little bit. So that's what's making this problem so hard. So the next thing I'm looking at, this is why my figure is so important. I'm staring at that ABCN, and I'm noticing it's modified by 62 degrees, and it's going left and down. So its X is negative, its Y is negative. 62 degrees. So what does that mean? It means if I come back here, that this is the just ABCN, but modified by the sine of 62 degrees, and it was negative, so it's down. And this one up here is ABCN as well, no more X. But it's modified by the cosine of 62, and it's facing left, so it will be negative.
Question. For ABN, you got 5.1,
Yes, I did.
and for ABCN, 1.04.
Yes.
Okay.
Nice job. That was a lot of painful work, but do you notice that it went from 2 equations at 8 unknowns down to 2 equations, 4 unknowns? That's progress, but we're still not there. Because notice that first column is ABT, ABN for both of these, ABCT, ABCN. So there's actually 4 unknowns. So that's kind of cool. But that's still not ultimately cool because I'm not going to be able to get this unless I get 2 equations, 2 unknowns. So you apparently survived this, Evold. So what's my next? How do I make any progress? Because I'm kind of at a stopping point now. Does that make sense? I'm like, oh, I did everything I can do in that figure, and I'm out. I'm out of moves. I'm done. Like, what do I do?
It's a cheat sheet time.
Mm-hmm.
Yep, and you go into the normal acceleration, and it's velocity squared over radius. And we do know 2 velocities, which is velocity of B and velocity of BC. And we know radius, which is one is going to be 1.25. The other one is going to be 3.25.
That's right.
Yep. And after that, we're going to have only 2 equations, 2 unknowns.
Correct. So let's do that. So I know the velocity of AN, which is an angular acceleration of n. So this would be the velocity. And so how do you decide what goes where? Like, what are the labels for these things? Because I'm thinking I've got acceleration of n and I've got acceleration of b with respect to cn. So maybe in terms of the picture that I wrote above, instead of just calling this acceleration of n, I call this acceleration of bn. So do you notice, like, there's acceleration of bn, there's acceleration of bcn. I can know something about those because normal acceleration is equal to v squared over r. Well, if this is b, if this top one is b, then this is velocity of b. If this bottom one is b with respect to c, then that's the velocity of b with respect to c that's squared. So, and you're exactly right in the sense that we just found the velocity of b. That was 2.53. And again, the velocity of b is associated with, here's the velocity of b. Velocity of b is associated with the radius that's perpendicular to it. So that's the radius I need right there. That was the 1.25. So that's exactly right. So this is 1.25. That comes out approximately 5.11. That would be feet per second squared. And velocity of BC, we just figured out was 1.84. So that'd be 1.84 squared. Again, over its radius, which was the 3.25 answer. So we're getting approximately 1.04. Again, feet per second squared for that. So does it make sense that I can now replace this and this, which just got rid of one of my unknowns. So now I have two equations, three unknowns. And then I can take this one over here and place it right here and right there. So now I actually have two equations, two unknowns. Wow. My brain is in pain. So when I wrote the two purple equations down, what that amounted to is, in a sense, I now have four equations, four unknowns. Because I substituted them in, I'm down to two equations, two unknowns. So because I'm afraid I'm gonna like make a mistake, do you see how easy it would be for me to lose that -2 up there? In my case, like I'm sort of a little concerned I'm gonna blow it. So I'm gonna rewrite this. So I have sort of my first equation was negative ABT times the cosine of 20. And now I learned that that is plus 5.11 times the cosine of 70. And that is equal to -2, didn't forget it, plus ABCT cosine of 28. How come I'm running out of room this time? Fit all so much better before. Minus 1.04 modified by the cosine of 62. So there's an equation with two unknowns. And I rewrite the second one, which was negative ABT modified by the sine of 20 minus ABN, which we just figured out was 5.11 modified by the sine of 70 equals 0. And then my ABCT is modified by the sine of, it says 8, but it can't be 8. So I obviously didn't write that very well. It's probably 28, but I'm in great danger here. Let's see, it was 28 right there. So that means it's supposed to be 28 right here as well. So modified by the sine of 28. And then finally minus ABCN, which we just figured out was 1.04, but that was modified by the sine of 62. to check my work, I'm just looking at what I saw before, which is just because it'd be easy to make a copying mistake, but it's like cosine of 20, sine of 20, cosine of 70, sine of 70, cosine of 28, sine of 28, cosine of 62, sine of 62. Okay, that's good. I assume you're sticking this in the matrix. Is that true for everybody? And by the way, I would just type it in almost just like it sits. I say almost because you'd have to move these to the other side and then move the constants over, like 5.11 times the cosine of 70 is over here.
Okay. So obviously, I have the acceleration of C or B. So I'm rotating. Shoot.
I got a negative acceleration ABT, I should say. I don't know why.
What'd you get?
Negative 1.9.
That's right. So what does it mean that it's negatively accelerating?
So it's negatively accelerating. So it's a deaccelerating.
Yeah, it's just slowing down.
Okay.
So it's got a speed. So you got that for BT.
Yep. And ABCT, it's positive 6.84.
Yep. So that means that's speeding up. So at this snapshot in time in which this picture is given, that means this speed that you got right here, which we figured out, I forgot what it was, velocity B, whatever that was. 2.57 was it? 2.53. That speed is in the process of slowing down right now. Whereas this speed, the speed here is actually in the process of speeding up right now. Notice those are actually speed changes because they're tangential, they're speed changes. So you're literally getting speed changes for this.
I really like this question.
Yeah, I mean, it's like love-hate, right? I mean, it's really cool. I mean, to be able to get something like this correct, I mean, you have to really go slow. You have to really write things out. You have to be super careful. You have to have kind of a system. That's what Landon's working on. You have to have kind of a good system for keeping track of stuff. You got to have a good drawing. But to think that you can actually figure all this stuff out, it's just kind of mind-boggling.
So this is going to be a test question, right?
Yep.
Yep.
Yikes.
But I don't know if I still have it up. I do. Take a look at yesterday's introductory question. Why did it take kind of less trouble? Well, because of the position that I put B in. Does it make sense? We didn't have to do as much modification. Our equation was much smaller because velocity of B was horizontal already. So it didn't have an X and a Y component. It just had an X component, and I didn't have to multiply by the cosine or sine of some angle. So
is that what 16,100?
Yeah.
Okay.
Yeah, it's part of why I'm really trying to get the cross product to work here. Because it's theoretically going to save me a massive amount of time, but in practice, I still have it.
So what I'm saying is on a test to save you some of the, because would you agree that the chances of getting this actually correct on your first try without checking and kind of in a test environment, even if you're comfortable with this, I'm doubtful that I'm going to get it right. It's not because I don't understand it. It's just there's a lot of moving parts, right? So, I mean, all I got to do is lose track of something. So, does it make sense if I put the location of B right there? That'd be a nice place to put it too, because then it would only have, a vertical component and no horizontal component. So there's some things I could do on the test to make your life a little bit easier. But
Yeah.
I don't know if you noticed, but that's different on this problem. And we were just practicing now, but I put B in a random location. So in a sense, I made this, I guess you could say, as hard as it could be. Well, I guess unless I, made the cylinder facing this way, and it was kind of like that was the velocity of C, and that was at some weird angle so that it wasn't as easy. Like when we got to the stage where we started plugging in the acceleration of C, the fact that it was just left and right and up and down, it was already kind of set up for that. That's kind of nice, but
I don't know, but the picture you're sharing right now, I mean, at least it's for me. I'm just seeing the not finished two equations.
are you seeing me right now?
Oh yeah, I'm seeing you, but at the same time, the screen you're sharing, there's like two equations that are not finished. I don't know if you're trying to maybe show something else, but
You should be seeing the final answer to these questions, the two that you just told me.
oh yeah, I
Hmm.
don't know. Landon, what are you seeing?
No, I'm seeing what you're still seeing.
I'm seeing this two horizontal and vertical to acceleration equations that are not finished.
Let me stop sharing and reshare. Maybe it's overloading for some reason.
Here we go.
Seem to fix it. So it is interesting.
Oh,
Thought, comment?
oh, I've got the answer. I just need to actually.
Are you saying you have your crazy plan is working?
Yeah. So basically, I was thinking about what parts I really needed, essentially, and if you really think about it, to get the normal and tangent components, or I'll just break it out a little more. To get the normal component, all you really need is the angular velocity and just the position vector which are provided, and then we already have the acceleration of acceleration at C. So then all we really need to find is the angular acceleration of the body, which is, in the equation, it's going to be the angular acceleration crossed with the position vector. Plus, then we just have to have the last acceleration, essentially, the actual acceleration at B that we're looking for.
Love how you're thinking about that. That's super cool.
So then so where I was kind of getting stuck was, well, I still both don't have the angular acceleration of the body, and I don't have, I was thinking of in terms of like a sub b in x and a sub b in y, but I can just, if I have the angle of the acceleration, then I can just turn it into a sub b, and then then I'm down to back down to two equations.
Yeah.
Two equations, two unknowns, and I can solve for that.
You're not wrong.
So I can't completely computationally go through it after making an initial drawing, but
yeah, but you're conceptually making sense of it. Well, just because it's fun to add, let's add this last element. So given that just like the velocity, the linear velocity and the angular velocity are related, the linear acceleration is related to the angular acceleration. And that's alpha as a letter, A for acceleration, A for alpha. So that's why they're picking that letter multiplied by R. So that means if I'd like to know the angular acceleration, then I could just take linear acceleration and divide it by the radius. So if I want to know the angular acceleration of BC, for instance, how fast is that connecting arm rotating? What's its speed change? Then I can say, okay, well then that'd be the linear acceleration of BC divided by the radius of BC, which was the long one, that was the 3.25. And we just figured out that this was 6.68, 6.86 or 6.84, just depends on how you rounded it. So BC, it is BC, isn't it? Yeah. So that's kind of cool to figure out. So I don't have it written down. So when you figure out 6.86 divided by 3.25 is about 2.11. And again, if we wrote the units in there, we'd end up with nothings per second squared. So this is radians per second squared. So that's kind of cool. And similarly, the angular acceleration of B would be equal to the linear acceleration of B divided by its radius, which is 1.25. And we just figured that out as negative 1.93. So I divide that and I get about negative 1.54. So it is, and again, I stop and think about what that means. What that means is the angular speed of that, I'm looking at the 1.54 right now. That means the angular speed of this, we know this is going in this direction right now, but it's in the process of slowing down because we just got negative 1.5 radians per second. So every second it's going to slow down by 1.5 radians a second. So it's in the process of slowing down right now. It'd be super fun to be able to have a good animation of this. So I could actually watch it slowing down, if you will. So that's what acceleration is telling me. And then the other one though was actually positive. It was 2.1. And so we said this was actually rotating in this direction, if I remember right. And it's in the process of speeding up. Like that's actually starting to go faster. 2 radians a second. 2 radians is about 90 degrees. So it's actually really picking up speed right now. That's actually starting to rotate faster. That's kind of interesting to stop and think about what the numbers mean that I just calced. We just calced. So I think what we need to do is Tuesday when we get together, just review, like roughly review Tuesday, take the test Thursday, I think makes the most sense for next week. That we have sort of plenty of time to kind of try to process this.
Yeah, I kind of wanted to ask about last class I mentioned on the homework, problem 111. The method for actually finding the velocity at B. And when you think about it, like just looking at the problem, I could post a picture of it actually. If I have one accessible, well, it's just all drawn over, but whatever. I'll upload this real quick. So let's chat. when you think about it, it kind of a lot like in a lot of ways this is a really simple problem because it's when you kind of have to run through it, it makes sense that the how do I put this, that the velocity of B has to be the same as the velocity at A, because at the top of the arc there.
Mhm.
And going,
Why do you say that though? You said it makes sense. Why does it make sense?
because at that exact moment it's traveling exactly tangent to a circle there.
Mhm.
So it, by definition has to be have no velocity in the y, which is nice, and it kind of simplifies the problem a little bit, but it also took me a lot of time to figure that out. I remember I
Yeah.
was mentioning the trying a couple of different methods to try to get through this, and you mentioned that the method I stumbled on was the one the book method had.
Mhm. Yeah,
But
that they have an infinite radius.
I don't love the math on that, to be honest.
Yeah, sure.
Like, you get a situation where you're the velocity is, it's the velocity is equal to the, sure was the math, or so the angular velocity is equal to the velocity over the length of the over the basically the radius from the center of the circle.
Right.
So you get your angular velocity is equal to 4 over infinity for one of them. So the other one is also 4 over infinity, and that I mean it makes sense, but also this part of me that wants to say, sure, it is 4, but couldn't it be any other number as well?
Gotcha.
And that like I don't like it.
Yeah, well,
really not.
That gets to the theoretical concepts of calculus when you start going down that road, because it's kind of about unlimited approaches. Because you're right. It's if you think of infinity as a number, then it could be 5 over infinity, 6 over infinity, but ultimately infinity is not a number. It's more like instead of 4 over infinity, it's 4 over n as n gets close to infinity. And so then you can treat n like any other number.
Yeah.
So one of the things I want to point out to you guys, though, is in a sense, I actually taught you this way harder than what's in the book. And the reason I did is because this problem isn't very realistic, and it actually introduces problems that make it really complicated. You can see here that they were trying to help by keeping it really simple, but it actually causes a lot of problems, and it doesn't allow you to kind of do anything. Like the problem we just did, it was just terrifying and horrible. Yet, if you can at least see your way through it, you realize I just did the worst case scenario. I mean, there was angles everywhere, and things weren't moving kind of like you made it nice. And it's like, wow, I can do anything. Whereas the book problems were kind of understandably, we're like, wow, that's just going to destroy them. So let's not do that.
Yeah, this problem really messes with your head a little bit, because if you try to think about how it would actually move, then you're like, oh, as A moves right, then like AB will automatically have like rotated clockwise slightly to account for that.
Mm-hmm.
Or I can't remember, but but at this specific point, it's not actually rotating. So
right, yeah, right at this second, AB is not rotating. You're exactly right.
That's
the
annoying.
Angular velocity of AB would be 0. But as soon as we move her right a little bit, now B is going to have to drop, and A is not going to drop. But if B does drop, then that means you're right. It's actually going to be rotating counterclockwise. And so, again, it's interesting about this whole snapshot in time concept, which again, I think is very depressing, but it's like we just spent an hour and a half trying to solve one problem for one snapshot in time. And now if we just let time go forward 1 second, we get a whole string of different answers. And so your desire to automate this process, Landon, I think is really cool. It'd be really fun is to kind of do this all in Desmos and then animate the point, and then just watch even if it was just numbers and not a visual animation, but then just watch the velocities grow to a peak and then get smaller. And same with the accelerations. If the velocity was growing, then the acceleration would be positive. If the velocity was constant, then the acceleration would be 0. If the velocity was decreasing, then the acceleration would be negative. And so just watching them all interact with each other kind of live instead of just a snapshot in time would be, really powerful.
Yeah.
Or even the problem that you just did right here. If you did it right now, and then you said, okay, let's move it 1 second. And 1 second is a lot because 4 meters a second means that A moved 4 meters. So that's probably too much time. But even if 0.1 seconds go by or something of that nature, and then redid it and saw like another set of numbers, but it was close enough to the original set that it would kind of like, oh yeah, that makes sense, that it would be, increasing in speed and decreasing in rotational speed and all of that.
Yeah, it kind of it bothers me that I can't figure out a way to solve this that isn't this. Like I can't find a mathematical, like a more purely mathematical approach for finding the velocity at B using other methods, and that kind of bothers me, honestly. Because the usual method of finding like VB equals VA plus the other parts of it, the rotation, I still don't have the rotation, so, and I don't have like other parts of the problem I can look at to create a system of equations that I can readily see. So maybe some yeah.
Well, with respect to your overall grade in this class, I don't know when you put time into that or if you even do, but I can change your grade up to a week or so beyond the end of the class. And so if you come up with a way to automate that, ideally maybe after the test so that you at least kind of survive the test and so forth. That'd be awesome, because I agree. And you're right, absolutely right. That's why vectors are so powerful, because if you can list them all that way and then automate the processes with dot products and cross products and those kinds of things, especially if you can get machinery to kind of calculate that for you instead of you actually having to take the cross product yourself, that would be even funner in terms of watching it all work.
Yeah, I want to say I can get MATLAB to do it for me, but it'll be involved. Like it'd be just as much setup for each individual problem than like